Welcome to Scaling the Security Researcher to eliminate open source security vulnerabilities once and for all. My name is Jonathan Leitschuh. I'm a software engineer, software security researcher. I am the first ever Dan Kaminsky Fellow. I'm a GitHub star, GitHub security ambassador, and you can find me on Twitter at @Leitschuh and on GitHub at the same handle. So before I start, I just want to put a brief disclaimer up. First off, I'm sponsored by GitHub. They give me a little bit, so I just have to state that legally. And then also, we do discuss a SaaS tool in this talk, but it's available for free for open source, and you can use it in your open source research as well. This work is supported by the Dan Kaminsky Fellowship at Human Security. For those of you who don't know Dan, Dan was best known for a massive vulnerability that he found in DNS back in 2008. He was also known for his kindness and compassion in the information security community. He tragically passed away last year, and the Dan Kaminsky Fellowship, I also never got to meet Dan, unfortunately. And the Dan Kaminsky Fellowship was created to celebrate Dan's memory and legacy by funding open source work that makes the world a better and more secure place. And so this is the work that I've been doing for the past year under this fellowship. Spoilers. I generated a bunch of pull requests to fix the vulnerability zip slip across the Java ecosystem. In particular, I generated 152 pull requests across the Java ecosystem. But there's a lot to this story, so let's talk about how we got here. This story of bulk automated pull request generation to fix vulnerabilities at scale started with a simple vulnerability. And the vulnerability was this vulnerability. It was the use of HTTP in my company's Gradle build to resolve dependencies. And I found this code, and I'm like, how did this code get here? And the reason that it got here was I'd copied and pasted this chunk of code from an open source repository. And the reason that HTTPS is important is because if you don't use HTTPS in your build infrastructure, you can result in an attacker in the middle vulnerability, and they can compromise the contents of your artifacts in flight and compromise your supply chain, your CI/CD pipeline for your project. And this is an example of that same vulnerability existing in Maven, where it exists in the download for your dependencies that are used for the compiler and test dependencies. And so if that jar file is compromised mid-flight, it can result in it being you having malicious code executed in your CI/CD pipeline or on your developer machines. And this is an example where it exists in artifact upload, which usually is associated with credentials. And so an attacker could use those credentials to replace artifacts on your artifact server. And this vulnerability was everywhere across the Java ecosystem. It existed in projects like Spring, Red Hat, Kotlin, Apache, JetBrains, Jenkins, Gradle, Groovy, Elastic, Eclipse Foundation. It also impacted Oracle, the NSA, LinkedIn, and Stripe, so organizations around the industry. Maven Sonatype is the NPM to the JavaScript ecosystem or the pip to the Python ecosystem. Sonatype is that to the Java ecosystem. And when I reached out to them, they said that 25% of their traffic was still using HTTP to resolve dependencies instead of HTTPS. This is in June of 2019. So how do we fix this vulnerability? I pushed forward an initiative that on January 15th, 2020, all the major artifact servers in the Java ecosystem would decommission support for HTTP in favor of HTTPS only. And the major artifact servers decided, yes, we will do this, and they published their blog post announcing that they would do this in a coordinated manner. However, I reached out to Sonatype again, and in January of 2020, only a few days before the planned decommission of support of HTTP in favor of HTTPS only, they said that 20% of their traffic was still using HTTP. So you can imagine what might have happened on January 15th, 2020. Broken software everywhere because suddenly people's builds stopped working. But this stopped the bleeding. Sorry. Hang on. We stopped the bleeding. But what about the other repositories? So these are only the most commonly used repositories in the Java ecosystem. Maven, JCenter, Spring, and Gradle plugin portal. Other organizations in the Java ecosystem host their own artifact servers, and they're unlike NPM or pip, where there's one central repository. The Java ecosystem has been around for a long time, and so multiple other repositories have evolved to be used by organizations around the world to host artifacts. So how do we fix the rest? And I said, well, let's just go to the source of the problem, and let's just fix it in the repositories themselves. Let's try bulk pull request generation to fix this vulnerability. So how? Well, the first thing that you need to do is you need to find the projects that are vulnerable. Because I knew that it was everywhere, but you need a list of vulnerable projects. And so for that, I wrote this CodeQL query. And it's a very simple little bit of code, but it finds this vulnerability in Maven POM files. CodeQL scans hundreds of thousands of open source projects, and you can use it to find vulnerabilities across open source. And for this very simple query, GitHub awarded me a $2,300 bounty. And so that gave me a list of projects that were vulnerable to this particular vulnerability. And then I wrote a pull request generator to generate the fixes, to generate the pull request to fix this vulnerability. And so the first pull request generator was Python-based. It was a wrapper over GitHub's Hub CLI. It had one nasty regular expression and a lot of logic for bouncing off of GitHub's rate limiter. And this is the logic. At a high level, it's got an underlying engine, but it has all the logic for the commit message and the regular expression that's doing the transformation, and the file, fixing the vulnerable files. And this is the regular expression. And the reason that I used a regular expression to fix XML files is that if you use an XML parser, any XML parser that you parse your source code into that XML parser and you make a modification will result in, when you dump it back out, will dump the source code, dump the code back out in the format of the parser, not the format the file originally came in as. And so if you don't use a regular expression, unfortunately, the XML that you'd end up having fixed the code in would end up with a massive white space change across the entire file. And the maintainer who would receive that pull request would be like, great, thank you so much for the contribution. You fixed a vulnerability, but you've changed the rest of the file, so we can't accept it. So you need to make targeted changes, and so that only leaves you with regular expressions, unfortunately, to fix this problem. But the problem is if you use regular expressions to fix a problem, now you end up with two problems, the regular expression and the problem you originally had. Regardless, though, it worked. I generated pull requests, lots of them. And here's an example of the diff that was generated. You can see the simple replacement, uses of HTTP and HTTPS in the correct locations in this Maven POM files. And I generated 1,596 pull requests across the Java ecosystem. And this was back in 2020. As of 2022, there's been about a 40% merge rate of all these pull requests at this point, which is a pretty significant number of vulnerable projects fixed across the Java ecosystem. And for this work, GitHub awarded me a $4,000 bounty from the GitHub Security Lab bug bounty program. So I got hooked on this idea of bulk pull request generation as a solution to fix vulnerabilities at scale across open source. This is my GitHub contribution graph for 2020. And you can see there's two major peaks where I did these campaigns, and so it's really cool to see the visual representation of the work you're doing. So I have a problem, and the problem I have ADHD, and that's not my problem. I don't believe that ADHD is a problem, but the problem is I love chasing squirrels. I love chasing vulnerabilities and learning about them. I will read GitHub security advisory feeds or advisory feeds, and I'll be curious about a vulnerability. And I can find, if I use GitHub CodeQL or if I use GitHub Code Search, I can find those vulnerabilities everywhere. So the problem that I have is because I chase squirrels, I find too many security vulnerabilities in open source. As an example, This is a list of vulnerabilities called zip-slip, and we're going to get into what zip-slip is later. I know I've mentioned it twice now. I'm going to mention it a bunch more times. We'll dig into what zip-slip is for those of you who don't know. But this is a pretty critical security vulnerability, and there are pages and pages and pages of this alert for this vulnerability in open source that you can find just by going to lgtm.com and punching in zip-slip. Like, there's more of this than I can reasonably report in open source. So I'm finding too many security vulnerabilities. So how do we get these vulnerabilities fixed so they don't just linger there? We need automation to fix these vulnerabilities, to actually get them fixed and not just be alerts. And so this is where I need automated transformations at massive scale. And so this is where Open Rewrite comes in. Normally, when you're compiling source code, you have the compiler produces what's called an abstract syntax tree. It's a code or tree representation of the source code. And so if you want to make modifications to that AST, you can, but the problem is that if you were to dump that AST back out into source code, you'd lose all the formatting. You'll notice that the spacing, the tabs, the comments, all of those things are gone because the compiler doesn't care about those things. And so what Open Rewrite provides is a format-preserving abstract syntax tree. And so the source code and the tree map back and forth to each other. They are the same thing. You can transform back and forth between the two of them. And in addition, you can generate new code that looks like the surrounding code because as the parser is running and as the formatting is getting grabbed, you're also capturing the white space, the tabs, what the style is from this code base. And so it learns what the code base is, and so it can generate new code that uses the tabs or uses spaces. And it's also fully type attributed. So the reason that's important, right? We don't know just looking at this code, is that log4j, SLF4j, log back, right? That might be really critical to know what type that is. I can't imagine there ever being a massive security vulnerability in a logging framework that impacts the entire industry. Log4j, anybody? And also, Open Rewrite's AST is both syntactically and semantically aware. That grid on the left side is the amount of data that's there's actually 6,000 nodes missing from that image on the left because it would just be fuzz. So with the amount of data, you end up with a lot of data and a lot of ability to manipulate that data to do cool transformations. And then if you want to add new code into the AST to modify it, the problem is that even simple little changes in code create complex ASTs. So let's say that I want to inject this little bit of code to fix a vulnerability, the vulnerability zip-slip. This is the code that you want to fix this vulnerability. Well, you need to place this in the code in the context of the surrounding code. So Open Rewrite has a templating engine. And the templating engine allows you to have variables, and it also comes with a coordinate system that lets you state, I want to place this chunk of code into the AST after this statement. And that unlocks us the ability to specifically target a specific location in the AST and generate and add that fix in. And this is the fix for zip-slip. And again, we'll go into what zip-slip is in a little bit later. So what's possible now? What other vulnerabilities can we fix with the unlock that Open Rewrite provides? I'm going to talk to you all about 3 vulnerabilities: temporary directory hijacking, partial path traversal, and zip-slip, and how I applied Open Rewrite to fixing these vulnerabilities across open source. So the first vulnerability we're going to talk about is temporary directory hijacking. Temporary directory hijacking, the temporary system temp directory on Unix-like systems is shared between all users. So, and the impact of that is if you write sensitive files to the temporary directory and you haven't set the correct POSIX permissions on those files, any other local users can view the contents of those directories, those files or directories. And this is temporary directory hijacking as it appears in the Java language, or, well, what you'll see. And the reason this pattern appears is that prior to Java 1.7, there did not exist an API to create temporary directories. So people created temporary files using the Java's temporary direct file creation API, which does create a CSPRNG securely generated name for the file, but then they'd call delete, and then they'd call makedir. And this has a vulnerability in it. And the reason that you'd find this code again and again and again is because if you said, I need to create a temp directory, how do I do that? And punch that into Google, if you'd ask Stack Overflow, you'd get vulnerabilities. And why is this vulnerable? Well, the reason this is vulnerable is because there's a race condition here. The race condition exists because makedir, if it fails because another user has beaten you to creating that directory, then it returns false. It does not throw an exception. So the fix, or one potential fix that you'll see, is people putting this makedir into a guard that throws an IO exception. However, this is insufficient still because that makedir call does not set the correct POSIX permissions. And so the contents of that directory are still exposed to other local users. And so it's still, this is still vulnerable to what's called temporary directory local information disclosure. And so what's the real fix? Well, the real fix is to use the new, well, very old, but the Java introduced in Java 1.7. Java 1.7 is very, very old. It's been around for a very long time. You can safely use this API. And this both creates a directory and also sets the correct POSIX permissions on the directory. And so I've gotten several CVEs for this vulnerability, and I figured, okay, let's see what I can do. I'm sure I've gotten a bunch of CVEs for it, but let's try to just fix this vulnerability across open source. And so that's when I applied temporary directory pull request generation. And for this particular vulnerability, I've generated over 64 pull requests across the Java ecosystem to fix this vulnerability. And so what does this look like? Well, you can see that we're deleting the vulnerable lines and replacing it with that one safe line. But also, you remember when I was talking to you about temporary directory information disclosure, we can also fix that by deleting those if blocks and replacing it with that one non-vulnerable line. And that's all due to the power of Open Rewrite. So vulnerability number 2 is a vulnerability called partial path traversal. And partial path traversal exists, let's assume that you have 2 users on a system. You have user Sam and user Samantha. And you want to sandbox, as a developer, software developer, you want to sandbox your logic to user Sam. Partial path traversal allows an attacker access to a sibling directory with the same prefix. So starting again, we have user Sam, and we've tried to sandbox our logic to only that. And user Samantha, the reason that an attacker could access user Samantha is because they share the same prefix. And so this is the partial path traversal vulnerability. Well, why is this vulnerable? Well, the reason that this logic is vulnerable is because when you call the method getCanonicalPath on a file, it returns a string that looks like this. And you'll notice there's something missing from that string. It's that trailing slash that was originally passed. And so when you call so getCanonicalPath does what you normally want it to do. It normalizes the path. It normalizes the path, so it removes the .. the path traversal payloads. But it has this characteristic where it removes that trailing slash that you need for starts with comparisons. And so when we have this parent directory, this intended sandbox directory, user Sam, and then we have an attacker payload come in, path traversal Samantha/Baz, when getCanonicalPath gets called on that, we end up with user/Samantha/Baz starts with user/Sam, and that does indeed pass. So this IO exception does not get thrown. And so what's the fix for partial path traversal? Well, the fix for this is that one solution is to re-add the file separator character back into the string for the starts with call. But the better fix is to use the Java path API, which was introduced in Java 1.7, which does these starts with comparison correctly on the correct path. So how do we find this vulnerability? So the way to find this vulnerability is to look for the Java string starts with call, and then look for the subject and argument where the get canonical path is the argument being passed. But we want to make sure that we're not fixing non-vulnerable code. So we also want to look for cases where that file.separator character is passed and not fix it in this case. But it can't be that easy, right? Well, developers write code in a lot of different ways. So what if the developer writes their code like this, where they extract that get canonical path to a variable, or they put the parent into a variable as well? How do we, or they put the safe version like this. How do we determine if this is vulnerable or not in this case? Well, we need this new concept. It's called data flow analysis. Data flow analysis allows us to track the variable assignments of the data as it flows through the application, as we're looking at the AST in the source code, as we're making the modification. And it lets us track, that this variable is safe, so we don't need to fix this vulnerability. And data flow can even handle intermediate variable assignments as well. So data flow uncovers hard-to-find vulnerabilities and helps us prevent false positives. And as a show of hands, have any of you written CodeQL? OK, so if you've written any CodeQL, this API for data flow analysis is designed to be very similar to CodeQL's data flow analysis, because I've written CodeQL before. Also, let me translate my knowledge easier. But hopefully, your knowledge can be transferred easier as well by using this API. And so when we put all this together, you can find that this is vulnerable, this logic, and fix it appropriately because of the data flow analysis. I want to talk about an example case. There was a vulnerability in the AWS Java SDK. And this is the vulnerability. You can see the partial path traversal vulnerability right there, because there's that starts with call on get canonical path. They were using this logic to determine if as you're downloading the contents of as you're downloading the contents of an AWS bucket to your local machine, the entire contents, is the AWS bucket key a path traversal payload that is attempting to escape the destination directory? And so they were using this logic, leaves root, as a guard that tries to make sure that that does not happen. And so they did fix it. There is a CVE. But of course, a little bit of vulnerability disclosure drama plays out in any good story. The AWS team said, "We'd love to award you a bug bounty. However, we need you to sign a non-disclosure agreement." And I said, "I normally don't agree to non-disclosure agreements. Can I read it before potentially agreeing?" And the AWS team came back to me and said, "We're unable to share the bug bounty program non-disclosure agreement since it and other contract documents are considered sensitive by the legal team." For any of you who have played Pokemon. So yes, that was a little bit of... I still have not been paid by them. It's an ongoing story. We'll see what happens. So the third vulnerability is a vulnerability called zip-slip. Now, zip-slip, we discussed it a couple of times. Zip-slip is a path traversal vulnerability while unpacking zip files. Zip files are basically a key-value pair where the key is the file that you want to unpack to, and the value is the contents of the file. But the key, if it's controlled by an attacker because you've been provided a malicious zip file, could be a path traversal payload. And so this is zip-slip, this bit of code. Well, why is this vulnerable? It's vulnerable because you're using this entry, this named entry in the zip file, as the way to create a file. And so if that is a path traversal payload, it can escape this directory and overwrite the contents of bin bash or something similar, and that can allow an attacker to achieve remote code execution. So zip-slip is a critical vulnerability in the right scenarios. Zip-slip is complicated. And the reason that it's complicated is that this is a valid fix, but the problem is that although this is a valid fix, this is also a valid fix. And again, we don't want to fix code that's not vulnerable. So how do we determine if we're looking at this case or this case when we're looking just at the abstract syntax tree in code? And so we need this new concept, again, which is called control flow analysis. So control flow analysis allows us to differentiate between these two bits of code, the vulnerable and the non-vulnerable code. And control flow analysis is a graph. Its control flow analysis is represented by two primary data structures, basic blocks, which make up the set of contiguous operations that are going to occur in a program without a jump occurring. And then condition nodes, where conditional logic will occur and there will be a branch in the execution of the program. And so by generating the control flow graph for a program like this, we can look at the graph and determine that there is a check in place for this vulnerability, and so we don't need to generate a fix for this vulnerability. And so when you put this all together, we can determine that there is a vulnerability here and that we need to fix it, and so generate the fix for the vulnerability. And then we can even do more complicated things due to the power that Open Rewrite provides, and even clean up the surrounding code a little bit too. So let's get to the pull request generation part of this talk. If you have security vulnerabilities, everybody gets a pull request. So let's talk about the problems with pull request generation. And one of the problems you'll run into is how fast you can generate pull requests across GitHub. So when you're generating pull requests, you need to do there's 6 steps, and there's three major categories. File I/O, which is basically free because it's happening on your local machine. Git operations, which are free on GitHub and do not incur a rate limit. And then GitHub API calls, which are rate limited. So the first thing you need to do is check out the source code and download the code repository. And then you need to branch and apply the diff that was generated by Open Rewrite, and then commit the change. Then you want to fork the repository on GitHub, rename the repository on GitHub. And the reason that renaming the repository is important is because when you're generating tens, hundreds, or thousands of pull requests, you're going to end up with name collisions, and GitHub won't let you fork repositories when you already have a repository with that same name. So you need to change every repository's name to something that's unique. And then you need to push the change, and then you need to create the pull request on GitHub. And so you'll notice there are three API calls. And GitHub asks that you wait at least 1 second between each one of these. So that's 3 times the number of pull requests you're trying to generate, number of seconds. But then there's a secondary and tertiary rate limit that they document, which is one of them's a header that says, please back off until this point. And then a third rate limit, which is basically just stop for right now, and it's not documented like how long you're supposed to wait. So throw a sleep in there and hope for the best, basically, is what your best option is at that point. So GitHub, if any of you are in the audience, if you could stop rate limiting or limit the rate limiting of your API, it would be great. It would make my life a lot easier. So yes. So we've made it this far. The vulnerability's been detected. The style's been detected. The code has been fixed. The diff has been generated, and the rate limit has been bypassed. At this point, I'm going to introduce. So how do we fix this for all the repositories across open source? At this point, I'm going to introduce you to Modern. Modern is free for open source projects. They've indexed about 7,000 repositories, and it lets you run Open Rewrite transformations at scale. And it generates and lets you update those pull requests. There are over 800 recipes that Modern and Open Rewrite contain inside of it. And it lets you generate pull requests. One of the use cases, for example, is let's say you need to update your version of Spring. You can do that. But the problem is that if you want to use the latest version of Spring, and we all, as security practitioners, know that running the latest version of Spring in your Java applications is really important. Well, for a lot of developers, if you want to upgrade your version of Spring, you actually also have to upgrade your test framework. And the test framework, the latest version of Spring, will only be tested by JUnit 5. And there was an major API breaking change between JUnit 4 and JUnit 5. And so you may not think of your testing framework as a security like what version of the secure testing framework you're using is a security blocker to security, but it really can be when you can't upgrade the version of Spring because you're running your old tests. So there's an open rewrite transformation for migrating all your tests from a previous JUnit version to the latest version of JUnit. And it also enables bulk pull request generation for across either your organization or across open source. As an example, if you have a list of, this is an actual result set that I was going to generate pull requests for. You can say, I want to generate this pull requests as a fork, from a fork. You can set the commit name. You can set the pull request title. You can provide the commit title. You can supply your GPG key, and then off to the races. It'll generate all the pull requests for you right within the SaaS. So this is how I generated all these pull requests, the most recent set of pull requests. But there are more than just 7,000 repositories in the world. How do we find the other vulnerable projects? Well, this is where CodeQL comes in. CodeQL indexes 100,000 open source projects and 35,000 Java projects. So you can write a CodeQL query and get a list of vulnerable projects. And then using that list of projects that you now know are vulnerable, if you provide that list into this CSV file that's under this GitHub repository, Modern, after they've ingested this list, will begin to index those repositories, and you can run your recipes that you've created across these repositories that you've identified this vulnerability in. So finally, let's go generate some open source pull requests. And that's what I did. And some of the statistics, for temporary directory hijacking, I generated 64 pull requests with a 25% merge rate, 50 pull requests for partial path traversal with a 22% merge rate, and zip-slip with 152 pull requests with a 20% merge rate. Now, I haven't updated these statistics for about a month, but I did this campaign in August of this year. So the 40% merge rate was from 2019. So hopefully we will see more things get merged as maintainers notice their notification feeds and start merging pull requests. It just takes time at this point. But in 2022, I've generated 600 new pull requests. And in my history, I've generated over 5,200 pull requests to my name. One unlucky project was the recipient of all 3 pull requests. Yes. And this is my GitHub profile for this year. So let's talk about some best practices for bulk pull request generation. The first thing is messaging. You're reaching out to so there's this saying, all software problems are people problems in disguise. And we are automating the generation of pull requests to fix a vulnerability at scale. Maintainers don't like bots very much. Developers, they like real people, but yeah. So you need to be considerate of communicating both why you're doing this, but also the impact, and then I think that you're a real person willing to communicate with them. So very important to maintain that human element in this dynamic, even though you are throwing an automated solution at the problem. And so some simpler lessons: sign off on your commits. And the reason you want to sign off on your commits, this is what a git commit sign off looks like. You just put this in the commit body. And you might ask, well, why do I want to sign off on my commits? Well, there was a bunch of lawsuits in open source a few years ago. TLDR, lawyers. Otherwise, you'll get your commits rejected by evil dragon bureaucrats. Be a good commitizen. GPG sign your commits. This is what it looks like. It just adds that verified badge. Otherwise, you'll end up like Linus Torvald, who has been impersonated on GitHub several times. CCOM. CCOM is a commit format for commit messages for vulnerability fixes. So if you want a way to lay out your messages, this might be a good thing to use. There are lesson 4. There are risks to using your personal GitHub account. By show of hands, is anybody here familiar with GitHub's Angry Unicorn? No? Okay, only me. This is what shows up when you've broken GitHub or something's gone wrong. This is my GitHub profile for most of 2020. I broke my GitHub account. Although I did break my GitHub account, I still recommend using a personal account for this, as it keeps that human element involved in this dynamic. And maintainers are less likely to be upset if they're more likely to be upset if it looks like it's coming from a company or a bot than it is if it's coming from a real person. Lesson 5, coordinate with GitHub. Before attempting, reach out to GitHub. That's what I did. And let them know that you're going to do this. They want to know. They want to help you out. Lesson 6, consider the implications. Shortly after beginning this campaign, I received this issue against my GitHub account, Leitschuh /security research. Is this responsible disclosure? Now, I use the more nuanced term coordinated disclosure, but the answer is no. This is not responsible disclosure. It is full public disclosure of a security vulnerability in an open source project. You are ODAing a maintainer, potentially. Unfortunately, the alternative for me is to not report the vulnerability at all, because there's only so much time that I have in my day, and I am overwhelmed. And so I believe that this is a solid solution to fix these vulnerabilities at scale, and best use my time to actually get these vulnerabilities fixed. So in conclusion, as security researchers and security practitioners, I believe we have an obligation to society. We know these vulnerabilities are out there. We've seen them in pen test reports. We've written them up ourselves. We've been on the receiving end. We know how to audit this code. Spoiler, most software developers don't watch Black Hat talks or DEF CON talks or Code Blue talks. Most developers are focused on developing the code to the features that they've been asked to develop. There's this statistic that GitHub provided. For every 500 developers, you have one security researcher. We are heavily outnumbered as security practitioners. And so I believe, truly, that automated bulk pull request generation is the best way for us to scale our knowledge of math, science, technology to fix vulnerabilities across open source at scale and actually see these vulnerabilities fixed finally. And so with that, I want to leave you with one final quote. This is from Dan Kaminsky. It's on his Twitter profile, and it's there to this day. We can fix it. We have the technology. Okay, we need to create the technology. All right, the policy guys are mucking with the technology. Relax. We're on it. And so just some final things. Learn CodeQL. It's an incredibly powerful language. Contribute to Open Rewrite, and you can deploy your security fixes at scale. If you want to discuss this with other people, join the GitHub Security Lab and Open Rewrite Slack channels. And then also, if you're interested in open source security in general, consider becoming involved in the Open Source Security Foundation. There are working group meetings, not necessarily in the right time zone for everybody in Japan, but there are working group meetings that are happening on a daily basis or on a weekly basis to discuss the biggest issues facing open source security around the industry. And with that, I want to thank Human, my employer, for enabling the Dan Kaminsky Fellowship, Modern for working with me, Lydia Giuliano, the Black Hat speaking coach that I worked with, and Sham, my intern, who came up with some of the graphics you saw for control flow analysis. And this is me. So thank you all.